Okay, so what do we got?
Either Euler.
No, none of those are correct.
Euler.
Euler. It is Euler. It is Euler.
What?
I don't know. I don't know what language it is, but it's pronounced Euler. Euler's method, okay? So here's what, let me give you a brief synopsis of why Euler's method exists, okay? As we know, some differential equations are not separable, and you can't easily solve them, okay? The ones we've been looking at are. And so Euler came up with a method to closely approximate a solution of a differential equation when you can't separate it. That's what Euler's method is for, okay? And just like when we talked about integration, the first time you learned about integration and area under a curve, if you make the width of the rectangle smaller and smaller and smaller, you get a more accurate and more accurate and more accurate area. It's the same idea here, except instead of relating it to area, we're relating it to a solution curve. That's what it is, okay? So I'm going to give you some stuff to write down just to give you some context, and then we'll just get into it, okay? So, what I just said. It's a way to determine the curve of the solution to a differential equation more precisely than a slope field, because we make the change in x really small. Like on our slope fields, we usually make the change in x go by ones, maybe 1/2, sometimes by 2. All right, and then we kind of eyeball where the curve should be. Well, if we had the ability to make the x change by much smaller values, we would get a more accurate representation of the solution curve. And so that's what this is kind of all about. So to create the points for the solution curve, we need to calculate how much y will change after given a predetermined x. So they're going to tell us, we're going to be told what the change in x is going to be. And based off of that, we're going to calculate what the change in y will be. And that's how we're going to come up with the points in our curve. And the thing about Euler's method that's a little tricky is that our base, our reference is always, well, if x moves by this, then y moves by this. It's more complicated than that. Okay, so that's why we're gonna create this little table, and I'm gonna show you a good way to organize all your work, yeah. So ultimately, what Euler's method does is says, okay, if x changes by this much, you determine how much y is going to change. Right? And then, of course, we find this new y based on how much y is supposed to change. And that's how we come up with our values. This is all the big picture, big idea of what we're trying to accomplish here. Okay. Now, we're going to practice on some problems that actually are separable so that we can find the true solution at a given value and compare them. But ultimately, the point of this is to be able to do that with equations that aren't separable. Now, one of the more famous uses of this Euler's method, I don't know if, now I'm forgetting the name of the movie. The movie with the women who worked at NASA. What is it called? Hidden Figures, thank you. Okay. So, how many of you have seen that movie, Hidden Figures? Okay. If you haven't seen it, highly recommend. It's a phenomenal film. I don't know, obviously there's liberties always taken with those kinds of things, but the calculations that she was doing, Katherine Johnson is her name, that she was doing was all using Euler's method. And they talk about it in the movie. And now you can go back and watch it and they talk about Euler's method and they're like,
I can do the math.
You can, yeah, I mean, it was incredible how, I can't imagine she did it that fast. But, you know, that determining where they needed to be to get it out of orbit and back into the Earth's atmosphere was all done using Euler's method. All right, now I'm going to put some stuff up here that sort of shows you where the basis comes from. Please don't write it all down. at the very end, maybe the last part I want you to write down, but I'm giving you a real simple example of where this comes from, okay? As we know, we have our regular slope formula, okay? Don't write this down. You know your slope formula. And then we can rearrange it, right? And get it to places that sort of does us some good. Now, this is the one that I would like you to write down, okay? You're maybe not as used to seeing the slope formula in this form, okay? Your resulting y, take the y that you start with, multiply it by the slope and the difference of the x's, okay? That's just another version of the slope formula, and this is pretty useful to a form of it that we're going to use going forward. We're going to use it today for sure. So again, if you think big picture, what we're trying to do, we're trying to find what our new y is going to be. And we find our new y based on what the previous y was, change of x, okay? And so here's where Euler's method kind of comes. Okay, so that's our next y, our previous y. Of course, now we know slope is dy over dx. And then our difference of the x's is what we call delta x, or change in x. Okay? And it's going to have another phrasing that we're going to talk about here in a second that you're going to need to become familiar with. So we've taken something at an algebra level and changed it and start thinking about it at a calculus level. And these are going to be the things that we're going to use in order to use Euler's method, okay? The smaller the change in x, the more accurate our solution curve will be at any given point. So again, that's that analogy that I was making about integration, right? And the area under the curve. The smaller the rectangles, the width of the rectangles are, the more accurate our area is. The same way that we talk about that here. The smaller that change in x, the more accurate our slope, our solution curve will be. This delta x is often referred to as step size. That is a phrase you need to know. When they talk about step size, they're talking about change in x. So the step size will be given to you. They'll tell you what they want it to be, and then you will then find the y at some given point. Okay. This is the meat of the whole situation, right? If we can get our heads wrapped around this, Euler's method is not that difficult. And eventually, you'll fly through problems, okay? But the trick is getting the hang of, all right, what do I do first? What gets multiplied by what? Do I add something somewhere? And once you get the rhythm, and honestly, there's some rhythm to these problems. Once you get that, then these get really simple. Okay? All right. So, questions so far before we move on to some examples? Now, this is your book. I think I've tweaked it around a little bit, okay, to make it all fit the way I wanted it to fit. But there's two examples here, okay, and it's for the same problem, as I mentioned earlier. On the left, we're going to estimate the solution curve using Euler's method. Then on the right, the example 9, the problem is actually separable and differentiable, or able to be integrated. Okay, and so we'll find the exact value of what it actually is, and then on the left we'll do our approximation using Euler's method. Now, as I go through this and do this, if you need to write yourself little notes about the steps, here's what we did first, here's what we did next, because you write it down now and then you go back and look at it in several hours, you're not going to like, wait, which came first, which came second, which came third. And one of the things that you could do, just a suggestion, obviously they're your notes, do them how you want, you could color code it. I'm going to pick your color. Green is step 1, blue is step 2, red is step 3, and then you don't have to write yourself any notes. You make yourself a little key and you can kind of go from there. Because obviously there's a lot going on here. Okay? Now, the problem is we're going to construct an approximate solution. So remember, when we construct a solution, we're talking about a solution curve. For the differential equation, dy over dx equals y, we're going to start at the point 0.01. So they're going to give you a starting point, and the step size is going to be 0.1. So that's fairly small. Okay, x is going to change by 0.1. So where I like to start is with the information they give me. Okay, so the information they tell us right off the bat is they give us 0, 1. So that goes in the x and y column. All right. Now, the next easiest thing to do is, since I know what x has to change by, is I like to fill in the x column and just go right on down. I'm going to increase x by 0.1. All right, so this is going to be 0.1, 0.2, 0.3, which is not a coincidence that stops at 0.3, and it's asking for what is y of 0.3. That's not a coincidence. Okay, so then I like to fill those in. Now once we're in this initial setup, we work across, okay? Because we're going to find the change in y, right? That was the goal from the beginning. Remember that this is change in y over change in x. So if I multiply this by change in x, the change in x's cancel, and that's where my change in y comes from. This is the slope, okay? So if I take the slope and I multiply it by change in x, or dx, I'm left with change in y. And then I know how much this value needs to change by from 1, okay? So let's just kind of work through that a little bit. Now, they have to tell us what the dy over dx is, which they do. It's y. So in this case, what's this value right here? It's just 1, okay? It's the same value in this problem. Will that happen a lot? No, it won't. But for today it will, okay? So now what I'm going to do is I'm going to take my slope, right, and multiply it by the change in x. So the change in x in this, when I'm doing this calculation, will always be 0.1, okay? So it's 1 times my change in x, 0.1, which is 0.1. Now, let's understand what this 0.1 represents. And I actually graphed the 0.01, by the way. That's on here. Somewhere that was on there, okay? What this is telling us, what all this work does, what this calculation does, is it tells us how much y has to change by. Okay, and again, it's because I'm taking dy over dx times change in x, so the change in x is canceled, and I'm left with just a change in y. So, what I now know is what this value has to be. Since it's positive, I'm going to add it. Okay, so 1 plus 0.1. So my new value is 1.1, which means I also have a new point. Okay, so we're starting to develop our solution curve. So 0.1, 1.1. Now, because we're so zoomed out with this graph, it's not going to look curvy. All right, so now we go through it, and now it's an iterative process. Now we just keep going through it and going through the same thing. All right, so dy over dx is y, so this ends up being 1.1. Then I take that 1.1, multiply it by change in x, and then I get my new change in y. So notice how the change in y starts growing slower, right? So instead of it growing by like 0.2, like double or something like that, it only grows by 100. So that this number gets added to here, and I have a new y, and therefore I have a new point. Okay. Are we following? Do we have questions about what we're doing? Am I going too slow? Okay, you're okay. All right. So then, in this problem, my slope is 1.5, or did I just decide 1 again? I've got to multiply it by 0.1. You get what we're doing. I probably did. Okay. So my y is going to increase by 0.121. Now, I understand that on the AP exam, calculations like this don't necessarily have to be worked out. You should work them out. When you're doing a problem like this, you should work them out. because we want to make sure that our number seems accurate, okay? So there's how much my y increases by, and now we're done. Using this approximation, y of 0.3 is approximately equal to 1.331. And of course it's approximately equal to because we are approximating, right? So when I look at my graph, it looks kind of like a star, right? But we know it's because we're zoomed in. If we zoom back out a little bit, it'd probably look a little curvier, right? Since this equation is separable, we can find the actual value, okay? And we can see how far off our approximation is from the actual values. You won't always be able to do this. I mean, let's face it, if it was separable and you could integrate it and we could find the actual values, there's no reason to do any of this, right? But since this is your first crack at it, we want to be able to show you something and then compare it to and evaluate how accurate it really is, right? If it's accurate at all. So I want you to do that. I'm going to give you time to do that yourself. Solve this, find my y values, and let's see how they can compare, okay? So this is 7.1 stuff. Go. So of course we can move y to the other side. Ooh, did I leave off the dx? What happened? Did I forget that? Why did I do that? Why did I just write x? Should be dx. My bad. There we go. Then I integrate both sides. Okay, and then I've got my c value. Okay. Again with the e, right? So we gotta get an e in there. That's where my constant is going to come back in front. So we end up with that. And we can figure out what the constant is. Okay, in this case, since they give us the point 0, 1, okay, 0 goes in for x, so e to the 0 is 1, y goes in for y, so my second constant is just 1. All right, so we're working from this equation, y equals e to the x. Okay. So it's just a matter of plugging 0.1 in for x, 0.2 in for x, 0.3 in for x. Did you all get that? Okay, good. So there are my numbers, there are my values. So I mean, this is pretty accurate, right? It's pretty close. 1.1, 1.105, 1.21, 1.221, 1.331, 1.3. I mean, that feels pretty good, right? If we had our step size even smaller, made it go by 0.01, this would be closer to this, okay? And so that's the key. If my step size was big, then this would be further off than the actual ones. This is this, I mean, in theory, right? If I put this, made an equation out of it, and the slope, if I rearrange this equation, I get this. And that allows me to isolate the change in y. Okay, all right. On page, probably on the same page. Page. Example 10. I want you to do this one, please. From start to finish. They tell us the step size is 0.2. They give us a starting point, and we are not going to actually separate and differentiate. We're just going to do, I just want you practicing this. Go. All right. Here's what you should have done, something like that. Now notice here, one of the differences that happened is we started getting negative changes in y, right? So that means you're going to subtract. So the y started getting smaller and then started climbing back up again. If we kept going with this, right, it would definitely be more curvy and start coming up this way, right? That's the prediction. Questions about the process and what we did here? Now, we could separate this one and we could actually solve it, but we're going to tie it to our slope fields a little bit. So the next example, I thought, I'll put this up. All right, this is, I drew this particular solution curve. I think it's pretty close from the point 0.5. And then what we want to do is lay our graph that we just drew kind of over it and see where they line up and see visually how much of a difference there is in our slope field versus our approximated solution curve. Okay. And so I decided to take what I drew on the slope field and put it on the one that we already had. So you can see there's some divergence there. And maybe as we move further along the X, there'll be more divergence, but maybe at some point they will coincide again and get closer together. But there's just a kind of visual representation of the difference between the solution that we came up with using Euler's method versus the actual slope field, okay? And you could, if you really want to, go back and calculate to see how far off they are. But, you know, going back to Katherine Johnson, what she had to calculate, what I think what was happening, if I remember, and if I'm wrong, forgive me. I think the way that the ship was orbiting was elliptical at the time, and they needed to change it from an elliptical course to a parabolic course. And they had a phrase that I don't remember what it was. And so there was this, they called it go, no go. That's what they called it. So at go, no go, that was that like moment in time where they had to shift the ship from an elliptical orbit to a parabolic orbit so that it could come back down to Earth, right? And so what they were doing was trying to approximate when that needed to happen, okay? And so when, and they had a differential equation in order to basically change the slope, right? That's what they're talking about. If it stays in one particular orbit, it has that same slope the whole way around. Well, not the same slope, that's wrong. The slope would change in a consistent given way. And then they needed to alter it to change in a different way so that it would come back down from the atmosphere. Anyway, yeah, I definitely think, watch that movie again. One, it's an amazing movie. It's an amazing movie. It's really well done. And obviously I have a different sense. But now I think you would have a different appreciation for it than you would when you saw it a couple years ago maybe. So anyway, and then I pause and I look at the equations that they have on the board and like, is this just mumbo jumbo or is this a real math on the board? Like,
Is it real?